Okay, so next exercise 2. Now here we are given some polynomials over some finite fields, and we have to prove in the first 3 parts we have to prove that the polynomials are irreducible over their respective fields, and in the last one we have to prove that the polynomial is reducible, which means by definition reducible is a polynomial that is not irreducible over the field of integers mod 11. So let us see the solution. So we start by assuming that the given polynomial is not irreducible over the given field, and then we will try to arrive at a contradiction. Suppose x square plus x plus 1 is not irreducible over the field of integers mod 2. Then not irreducible means there is a factorization of this polynomial as a product of 2 polynomials, none of which is constant. Now in this case, since the polynomial is quadratic, it has degree 2, so that means if when we are writing it as a product of 2 polynomials, which is a non-trivial factorization, both of them have to have degree 1. That's because the sum of the degrees should be equal to 2. So that means this can be written as ax plus b times cx plus d for some coefficients a, b, c and d coming from this finite field J2, where to make sure that these are degree 1 polynomials, we have to assume that a and c are non-zero. Okay, then x square plus x plus 1 is equal to, we multiply the terms out on the right hand side and collect like terms. We will get acx square plus ad plus bc x plus bd which implies all the coefficients are 1. So AC is equal to BD is equal to AD plus BC is equal to 1. By the way, why do we equate coefficients when we have 2 polynomials equal? That's because that is the definition of equality of 2 polynomials. 2 polynomials are equal only when the corresponding coefficients are equal. Keep one thing in mind. This is not to be treated as a function of x, because we are now in a polynomial ring where x is an indeterminate. X has no separate meaning attached to itself. X is just a placeholder, right? So this polynomial can easily be thought of as something like this, where this is the coefficient of x squared, this is the coefficient of x, this is the coefficient of x to the power 0. So that's why saying that these 2 expressions are equal does not mean that 2 field elements are equal. This x is not to be considered as a field element in J2. This x is something which we don't know and which we will never know, and it is immaterial and it in fact does not make any sense to ask what x is. X is a part of the symbol that we use to write a polynomial. That's what x is. Okay, so that's why the coefficients are equal and we have got this. Now note that since a, b, c and d, these are elements in J2, so J2 we know has two elements. One of them is 0 and the other is 1. And here we confuse ourselves a lot because of these notations. 0 is not the number 0 and neither is 1. 1 is not the number 1. 0 is the congruence class containing 0 modulo 2 and 1 is the congruence class containing 1 modulo 2. Another way of saying this is that 0 is the set of all even integers, and 1 is the set of all odd integers. So if you really get down to what these things are, then these are sets. These things are just some symbols to denote these sets, and you can make sense of these symbols by considering them as the respectively the 0 element and the unique element in the field J2. Okay, and these equations also have to be made sense in that way. These are equations with objects coming from J2. So this one is the set of all odd integers. Now since a and c are in J2, so each one of a and c will take either the value 0 or 1. If any one of them is 0, then this side becomes 0 and we get the contradiction that 0 is equal to 1, which is clearly not true. So both a and c have to be non-zero, and the only non-zero choice for them, both of them, is that both of them have to be equal to 1, and the same applies to this one also. So b and d also have to be equal to 1. But AC equal to 1 equal to BD implies A, B, C, D, all of these things have to be equal to 1, and hence let's now concentrate on the third part of this series of equations. 1 is equal to AD plus BC. Now our A is 1, D is also 1, B is 1, C is also 1, and we have 1 plus 1, and in J2 1 plus 1 is equal to 0. So this is a contradiction. Again we have got C 1 equal to 0, a contradiction. So our supposition is wrong. That is x squared plus x plus 1 must be irreducible over J2. So that is part A. Like this we are going to solve parts B and C also. Here the argument has been quite straightforward. I mean, we did not have to work we did not have to work too much to get this contradiction. In the next part, or the part after that, there we have to do some more calculations to get a contradiction. So suppose x squared plus 1 is not irreducible over this time the field is the field of integers mod 7 j7, then x square plus 1, shall I be able to write it here? Let me squeeze it, ax plus b times cx plus d. Polynomial is still of degree 2, but the field has changed. Same conditions for some a, b, c, d in J7 where a and c are non-zero. Then, since we already have a calculation of this product, and here also we have the same expression, so we can use that directly. Then this time AC and BD are still equal to 1, but AD plus BC is 0. Because in this polynomial there is no x term, so AD plus BC is 0. Now 1 plus BC square. In place of 1 we can write AC times BD, because both of them are equal to 1, and we keep BC square like this. Now we take BC common out. If we do that, here we will have AD plus BC. Now you can use this one, this relation. So since AD plus BC is equal to 0, so this is equal to 0. So we seem to have got a solution to the equation 1 plus y square equal to 0 in the field J7, and this is a contradiction because this is not possible. J7 has 7 elements, and you can put each one of them in this equation and verify that none of them actually satisfies this equation. In other words, this equation is unsolvable in J7 for y in J7. So that is a contradiction. But one can directly verify that the equation 1 plus y square equal to 0 cannot be solved for y belonging to J7. This is a contradiction, and proves that our supposition is wrong. And I need ink. Is wrong. So x square plus 1 must be irreducible over J7. So this is part B. Then in part C, the polynomial is x cube minus 3 and the field is the field of all integers modulo 31. Suppose x cube minus 3 is equal to, okay, so now we have a cubic polynomial, a polynomial of degree 3, and such a polynomial, if it has a non-trivial factorization, then one of the factors, we have already seen this before, one of the factors with the polynomial x cube minus 2, when we proved that this is irreducible over the field of rational numbers, we started by supposing that it is not irreducible. That meant that it has two non-trivial factors. One of them is a linear polynomial and the other is a quadratic polynomial, because then the sum of the degrees will be equal to 3. So here also same thing, except here the field is different. So we will have a quadratic polynomial ax square plus bx plus c times a linear polynomial dx plus e. For some a, b, c, d and e belonging to the field J31, where a and d are non-zero. Here we have to calculate the product. Then x cube minus 3 equal to, okay, for x cube we have to multiply ax square with dx, that will give us ad x cube. For x square we can multiply ax square with e, that gives us ae, and we can multiply bx with dx, so bt x square plus, for x we will multiply bx with e, that gives us be plus c with dx, that means cd, and the constant term is ce, which implies, again we will equate like coefficients. So AD is equal to 1, AE plus BD is 0, there is no x square term here on the left side, and BE plus CD is also equal to 0, there is no x term either, and finally CE is equal to minus 3, which is it is minus, oh sorry, it's not minus 3, it is minus, okay, sorry about this, minus 9. I am not sure whether when I wrote the question down I wrote minus 3 or minus 9. If I wrote minus 3, please correct that. Okay, it's minus 9. In the last subdivision also it's x cube minus 9. then you can see that minus 9 is equivalent to 22. In fact, minus 9 is the congruence class containing the integer minus 9. That equals the congruence class containing the integer 22 modulo 31. And this equality actually is the equality between two congruence classes. And the reason for this equality is that minus 9 is congruent to 22 modulo 31. So this is equal to 22. Now we start with two things. One of them is b. b can be written like this. In place of b we can write minus a square e plus AD is equal to 1. So we can write BAD plus A square E. So these two things cancel out and AD is 1, so ultimately we get B. Now we can take A common out from the last two terms. Doing that we get BD plus AE. Now you can see that BD plus AE is 0, so this part will vanish and we will be left with minus A square E. So B turns out to be equal to minus A square E, and like that C can be written like this: minus ABE plus CAD plus ABE. Now we can take again A common out from the last two terms. So we will have CD plus BE. Again CD plus BE is also equal to 0. So this becomes minus ABE. We are now going to somehow use these expressions for B and C to conclude something. Then 22 is equal to CE. Now if you replace C with minus ABE, you will get minus AB E square, because you are bringing one E extra, one new E, and already there was one E, so E square. Now you can replace the expression for B. Minus A times minus A square E times E square. So this becomes equal to AE whole cube. Okay, but the equation y cube equal to 22. This equation has no solution in J31, and that's why we have a contradiction. Cannot be solved for y belonging to J31. This is a contradiction, and proves that our supposition is wrong. Hence, x cube minus 9 must be irreducible over J31. You may wonder how one comes up with these calculations, that is, how one knows what is to be done, and the answer as usual is no one really knows. When one starts a problem, there is no way of knowing how to proceed. In these cases, of course, you can start the problem by supposing that the polynomial is not irreducible, but after that, after getting these relations, you have to, the only thing you can do is that you can play with the relations and try to get some sort of equation which is not solvable in the given field. The somewhat hilarious thing is that, hilarious and at the same time frustrating and tragic thing is that when you are trying to prove something, okay, directly, then you won't get what you are trying to prove. Things will start to go wrong because you are trying to prove something directly, so you want your entire argument to be true. Okay, that is difficult in general. Very rarely do we come up with something original which is really difficult and it gives us a solution to some particular pretty difficult problem. On the other hand, if you are trying to prove something by contradiction, then you start by supposing the thing, that is the negation of the thing which you are trying to prove, and then you are praying that something goes wrong. In this case, however, everything goes right. Okay, you don't encounter anything wrong. Usually that's what happens when we are using a direct approach. Then things tend to go wrong, and when we want things to go wrong in a proof by contradiction, then everything seems to flow smoothly, everything is right. But this is just the way things are in mathematics. You just have to, it's a continuous struggle. You will come up with some solution, you will feel good about yourself for some time until you come across a problem which is pretty difficult. Then that will take your confidence level down. Again it will go up. So these ups and downs will continuously come like waves. You have to overcome these waves. It's frustrating. Mostly mathematics is frustrating. It's about perseverance and it's about coming back always. You can take a break for some time from solving a particular problem, but you have to come back to that problem with some new idea. Then only you can get some sort of success. And don't think that all these solutions are solutions that I have come up with without any help. I have taken help from the book itself. Sometimes I have taken help from the internet. If something is not yielding at all for quite a long time, then it's helpful to get some hints from the internet. And in fact, one of these subdivisions, I think the steps I have got from internet itself. So you should not consider these solutions as something that I am coming up with. Okay, I have already told this before. In fact, in my group theory videos, there is a solution that is so difficult, even Herstein himself was unable to do it in a particular way given some restrictions, but someone has done it and he has written a note about the solution. So while presenting that solution, I have credited that person. These things, however, which are available on the internet, it's very difficult to get the actual author. So you think of these things as done combinedly by all of us instead of by say only me or only you. Okay, we are all together in this struggle and we will reap the benefits also together. So we have done 3 parts. Now for the fourth part, the fourth subdivision, the polynomial is same, but the field now is the field of integers mod 11, and here we have to prove that the polynomial is reducible. Reducible by definition means not irreducible. We have, now here I am going to write a non-trivial factorization of x cube minus 9 directly. I leave it to you to verify that this statement is correct. Times x square plus 4x plus 5 in J11. You will multiply the terms out, fine, but keep in mind that these are not integers, these are elements in J11. With that thing in mind, you should be able to see that the right hand side ultimately becomes equal to x cube minus 9. So you can see that in this factorization both the polynomials are non-constant, so this polynomial cannot be irreducible, it is reducible. Hence x cube minus 9 is reducible over J11. So this completes the solution. Okay, now next exercise 3. Let f and k be 2 fields with f contained in k, and suppose fx and gx are 2 polynomials over the field f, that is they are coming from this polynomial ring, and these are relatively prime in fx. Relative primality means that any greatest common divisor of fx and gx is a non-zero constant polynomial. Actually we take GCD to be equal to 1, but that is equivalent to the GCD being a non-zero constant polynomial, that means being a non-zero field element, because I have already said that once in a Euclidean ring you find a GCD of 2 elements, then you multiply that GCD, keep multiplying that GCD by units, you get new GCDs. Okay, you get that many GCDs. For example, in the ring of integers, that is also a Euclidean ring, the integers 2 and 3 are relatively prime and their GCD is 1, that's why they are relatively prime. Now if one removes the restriction from the usual definition of GCD that we use in number theory of 2 integers to be a positive integer, if we remove that restriction, then -1 is also a GCD of 2 and 3, because it's a GCD, and that can be obtained from 1 by multiplying 1 by the unit minus 1. So the more units you have in a Euclidean ring R, the more GCDs you will be able to find out for two given elements. You multiply any one GCD by the units, you get other GCDs, and all GCDs can be obtained in this manner. That is, any two GCDs are associates. Any one of them is equal to a unit times any other. Now, in our Euclidean ring Fx, which is the polynomial ring, remember that in the very first exercise, that special exercise, we have proved that the units are precisely the non-zero constant polynomials, that is, non-zero elements in F. So, GCD of two polynomials being equal to 1 is equivalent to their GCD being equal to any non-zero field element. Okay, because of this relationship among the GCDs. Okay, so these are relatively prime in Fx. Now we have to prove that they are also relatively prime in Kx. Whenever GCD of two things is given, we almost always use the result that one can be written as a combination of the two things. This is true in general in a Euclidean ring, so it is true here also, since Fx and Gx are relatively prime are relatively prime in Fx, we have 1 equal to Ax Fx plus Bx Gx for some polynomials Ax and Bx in Fx. Now our aim is to show that a polynomial of what I'm trying to say is that they are also relatively prime in the larger polynomial ring Kx. It's thus enough to show that if dx, some polynomial in Kx, divides both Fx and Gx in Kx, then dx must be itself a non-zero constant polynomial. That will tell us that the set of all common divisors of Fx and Gx in Kx is the set of all non-zero field elements in K. So let dx be a polynomial in Kx such that dx divides Fx and dx divides Gx in Kx. This in kx part is important. The meaning of this relation is that fx is equal to dx times something. In kx means that something will have to come from kx. Then, in fact, that's what we are going to write now. Fx is equal to, say, what can we take? Let us take alpha x dx and gx equal to beta x dx for some alpha x and beta x in kx. Then we have 1 equal to, now we are going to use this equation. One equal to ax fx. In place of fx we can write alpha x dx. I should have, anyway it does not matter, I can write ax here also, plus beta x dx bx, and this is equal to alpha x ax plus beta x bx times dx. Okay. Now dx is a non-zero polynomial because we have chosen it to be a divisor of fx and gx, and divisors are never equal to, none of them is 0. So dx by our choice is non-zero, and this is non-zero, this polynomial, because otherwise the right hand side will be 0 and the left hand side will be 1, which is not possible. So that's why these are both non-zero polynomials, and as such we can find their degrees. Their degrees exist, and from the formula for the degree of the product of two polynomials we have this. This implies zero, which is degree of 1, so this will be equal to the sum of the degrees. Degree of alpha x ax plus beta x bx plus degree of dx. Now both these degrees by definition are non-negative integers, and their sum is equal to 0, so both of them have to be equal to 0. Thus, in fact, we don't care about the fact that this degree is 0. We only care about the fact that this degree is 0. Thus, degree of dx is equal to 0. That is, dx is a non-zero constant polynomial in kx. Hence, fx and gx are relatively prime in kx. So if we start with two relatively prime polynomials and we enlarge the base field, we take an extension of the base field, then also as polynomials in the larger polynomial ring, they continue to be relatively prime. So this completes the solution. Next, exercise 4. It has 3 subdivisions. Part A, prove that x squared plus 1 is irreducible over the field f of integers mod 11. Okay, and prove directly. Okay. That this quotient ring is a field having 121 elements. So this is part A. Part B is something similar, but the polynomial is different. Prove that x squared plus x plus 4 again is irreducible over f. The field of integers mod 11. And prove directly that this quotient is a field again having 121 elements. And there is a part C also, which is supposed to be somewhat difficult. So there is a star. Prove that the fields of part A and part B are isomorphic. Now there are some observations about this problem that we can make before solving the problem itself. You can see two things here. the way these two fields have been constructed or have been considered, we already know how they are fields. However, we have been asked to show directly that these are fields. Just like in the text we directly showed that this is a field. Much like that, here we have to show that both these quotient rings are fields. Now note that the number of elements is 121. So this is one observation. 121 turns out to be 11 square. We will prove at some point that every finite field has an order, if you call that order, of this form. That is, the number of elements in a finite field is always of this form, p to the power n, where p is some prime and n is some positive integer. Always, in the language of number theory, the number of elements in a field has only one prime factor. Okay, it does not have more than one prime factor. For example, you cannot have a field of order 12 because 12 is not a power of a single prime. It's 2 square times 3. We will prove this at some stage when we study field theory separately. The other thing we note is that both these fields, although they are entirely different, okay, this field has cosets of x square plus 1, this ideal, as its elements, but this field has cosets of this ideal as its elements. They turn out to have the same number of elements and they are isomorphic. This also in general is true. If you find two fields having the same number of elements, then they are isomorphic. So up to isomorphism, for a given order there is only one field. Okay, now I am not going to present the solution in this video itself. We will see the solution in the next video and we will see the other exercises also. We will try to complete this set of exercises. After this we will briefly go to group theory, but since many of you I have seen have become interested in ring theory, so I will continue ring theory alongside group theory. Previously I was doing them alternately, but now we will do it simultaneously. I will let you know at what time we will have the videos. Okay, and the other videos on analysis, calculus and contemporary abstract algebra by Gallian, those things will continue as usual. So with this I end this video. In the meantime, you think of at least parts A and B. At least try to show that these are irreducible over the field of integers mod 11. And if you achieve that, then try to think of how you can prove directly that these quotient rings are filled, which will require you to prove, just like how we did that one, that every non-zero element has a multiplicative inverse. That part is not going to be easy, okay, even in these two subdivisions where we don't have star, and this is going to be really very difficult. So you at least try to see how they are irreducible. Okay, so that will be enough, and then we will see in the next video the solution itself. So with that I sign off for tonight. If you are new to my channel, please subscribe to it. Consider subscribing if you find it useful. So that will be all. So this is me, Lucifer, from a mathematical room. Have a nice night.